said. We are here with Irina. She will be presenting Deepmind. So Deepmind is one of the Diamond sponsors, and thank you so much to Deepmind for all the support that they have provided throughout the organization of the school. So as a Diamond sponsor, the benefit is that they get to present a keynote on the machine learning projects that are developed in Deepmind. So, and we have with us Irina Higgins, a research scientist in Deepmind, to tell us about the projects that we developed there. Okay, thank you, Irina, for joining us, and please take over.
Thank you, Fiorika, for the introduction. It's really nice to be able to talk to you, although it's a shame that I can't actually see anyone. But I hope you enjoy the presentation. So it's going to be quite fast, so I obviously can't cover the full breadth of research that's done at Deepmind. But I'll try to mention a couple of our flagship projects and also talk a little bit about my own work. And I'll finish off with a quick story of how I got to Deepmind, because I think some people wonder, like, do you have to always study machine learning or computer science to work somewhere like Deepmind? Well, I didn't do that. My path was very convoluted, so maybe that will help out any of you who are wondering if they can switch fields. So as Viorka said, I'm a research scientist. I've been with Deepmind for almost exactly 5 years now. I started off in the neuroscience team, and more recently I moved to Frontiers, which is a team that essentially has people who don't fit the mainstream lines of work, like deep learning or reinforcement learning. So we have physicists, mathematicians, neuroscientists, and Frontiers try to do kind of more extravagant research, if you can put it that way. But anyway, let's start from the beginning. Why do artificial intelligence at all? And why was Deepmind founded? As you know, we live in a world which has a lot of problems, like from climate change to now kind of global pandemics. And obviously we have a lot of scientific problems, like how to cure cancer. And it's very hard to make progress in solving a lot of these problems. So the idea is that if we can develop an artificial intelligence system, then that's smarter than humans, then we can kind of parallelize scientific progress. Essentially, a machine doesn't need to sleep or eat. It can just be 24/7 trying to solve these big problems, and maybe it can find solutions that we as humans can't find because of particular limitations in our processing capabilities, our memory, etc. So at Deepmind, our mission consists of 2 parts. One is to solve intelligence, and 2 is use it to solve everything else, essentially all of these big problems that exist in the world. And actually, as a company, we're also broadly split into 2 groups. So one is fundamental research, where myself and Viorika are. And essentially, our goal is to build artificial general intelligence. And then the second group, we have people, for example, in the science team, who try to directly apply these techniques. And also, of course, they develop their own to solve very well-specified problems in science, like you may have heard about our protein folding project. Deepmind is actually celebrating 10 years this year. It was founded by Demis Hassabis, Shane Legg, and Mustafa Suleiman. Demis and Shane met in 2009 at the Gatsby unit at UCL, where they were both postdocs. And kind of a year after meeting, they've decided that it was time to make it happen, put the company together. And Deepmind was founded. And you have to, I don't know if you were even interested in AI back then, but even talking about artificial intelligence in 2010 was very out there. You know, people might think that you're a little bit crazy. So it was pretty incredible that Demis, Shane, Mustafa managed to get funding and get the company going, and actually let people believe the mission and understand that building AI is not something blue sky and out there, and it was real, and it was something that we could start working on already. So in 2014, Deepmind joined forces with Google because I guess Google also realized that artificial intelligence was very important, and it really helped accelerate Deepmind's mission. So it essentially went from about a few than 100 people to around 1,000 now since joining with Google, and we're still growing. So when it comes to building artificial intelligence, one of the first questions to ask is, what is intelligence, and how can we measure our progress towards artificial intelligence? So some of you may think, we can measure intelligence in humans. We have IQ tests. So why can't we just apply IQ tests to machines? The problem is that even measuring intelligence in humans is not simple. So this is a quote from Richard Gregory, who is one of the most prominent psychologists of our time. So he says, innumerable tests are available for measuring intelligence, yet no one is quite certain of what intelligence is, or even just what it is that the available tests are measuring. So that's quite pessimistic, right? And of course, IQ tests, they do measure something, and there are a lot of studies that show that whatever IQ tests measure correlates with academic performance, with a kind of general cognitive competence. But at the same time, IQ tests miss a lot. For example, they don't measure your emotional intelligence. They don't measure how fast you learn. A lot of things that are important for kind of defining what we mean by somebody being intelligent. So at Deepmind, we decided to adopt a different measure. This was proposed by Shane Legg, one of our co-founders. Essentially, this is the formula for intelligence that we're trying to maximize. Without going to the math here, we can rephrase it kind of as, we want to have a single algorithm that can learn to adapt and perform well across the broadest set of tasks. So let's kind of think, does this actually reflect what we mean intuitively by intelligence? So a human would be able to cook themselves breakfast, play chess, navigate a forest. They can do a lot, and they can do a lot of these tasks pretty well. So a human would be defined as intelligence according to this definition. But for example, let's say a cheetah, it will be really, really good at navigating its geography, its forest or whatever, but it will not be able to make breakfast or like cook eggs or play chess, right? So it will be really, really good at a narrow set of tasks than humans. So according to this definition, it will be less intelligent than a human. So that kind of seems in line with what we want to achieve with our algorithms. When it comes to building AI, what we use is a combination of deep neural networks and reinforcement learning. As you probably all know, currently deep neural networks are kind of the state of the art in terms of machine learning algorithms, and they are loosely inspired by the brain. So they consist of kind of artificial neurons, which of course are oversimplification compared to real neurons. And all these simple units are connected to each other, and the kind of information flows from the input to the output, and then at the output we compare what the network predicts with some sort of ground truth, with the true answer we want to achieve. And the error signal is backpropagated to the input to adjust the weights of the neural network so that it learns how to solve the task better. Reinforcement learning, you can think of it as a layer on top of deep neural networks. So our deep neural network is essentially an agent, and this agent is situated in some sort of environment. So there's a constant interaction between the agents and the environment. So the agent takes actions that in itself modifies the environment, and the agent receives new observations of kind of what has happened with the effect the actions had. The agent also has some sort of goal or task to solve. And so it might be taking random actions to begin with, but then at some point it might stumble across what it needed to do, and then the environment will give it a reward signal. And based on that reward, it can then learn that the actions it took prior to that were probably good, and they should be repeated again. So slowly the agent figures out what it needs to do and how to do it. And the difference between kind of classical supervised learning and reinforcement learning is in the amount of supervision that the agent gets. In classification or supervised learning, essentially for every observation, the agent gets an equivalent of a reward signal. It kind of gets the ground truth, it gets the teaching signal. Whereas with reinforcement learning, the agent might need to do a lot of actions before it receives any sort of supervision. And that makes learning much harder, because now you have to attribute kind of your teaching signal throughout time to actions you might have taken, thousands, sometimes time steps before the reward was received. But reinforcement learning is a very cool paradigm. So here's a very nice example where we have the same agent in both situations, on the right and on the left. So the actions the agent can take is the same. The observations, I guess, are the same, but the reward signals are different. And because the rewards are different, the agents learn different behavior. So it either learns to move forward or it learns to spin in place. So that shows how by shaping the rewards in the environment, we can achieve a lot of diverse behaviors by the agent. Okay. So before moving to the particular examples of where Deepmind's approach to AI worked really well, I want to tell you why we use games a lot. Because you will notice that a lot of what we've done is in game environment. So as I mentioned, the way reinforcement learning works is you have to take a lot of random actions before you stumble across your first reward and before you start learning. So that requires a lot of time to learn. And if you had real robots in the real world rather than game environments, you could have problems. So first of all, taking random actions can potentially break the robot or break the environment. You don't want a 1,000-ton industrial robot moving around randomly. You also want to kind of move fast and have a lot of experience to train from. And obviously with games, you can run them in parallel, you can run them faster than real time, but you can't go faster than real time in the real world. And also games are nice because they were created by humans for humans. So they reflect a lot of what's interesting about our world. And also they're meant to be interesting to play. So they're meant to stimulate intelligence. And they're obviously very diverse, and it's very easy to measure progress because typically in games you have some sort of score. So that makes games a very nice environment to develop AI agents in. And Deepmind has really excelled at that. So our 4 flagship algorithms are DQN, Alphago, AlphaZero, and AlphaStar. I will go into more detail about DQN and Alphago, but essentially Alphago is an algorithm that learned to play the game Go better than the world champions, and AlphaZero is a generation of that to other games like chess and shogi, and AlphaStar is an agent that learned to play Star Wars. So what is DQN? This was our first success story, and that's essentially what brought Deepmind onto the playing field. DQN is a reinforcement learning agent that learned to play Atari games. It takes as observations the frames of the Atari, and the outputs are the different actions you can take on an Atari joystick, and inside is a neural network. So this is what happened when we try to teach DQN to play Breakout. So at first it's taking random actions. It doesn't know what to do at all. But after a little bit of training, it's slowly is able to figure out the rules of the game. So it can it knows that it needs to bounce the ball. It then gets better and better. And at this point, it's already pretty much at the professional human level. But then unexpectedly to the researchers, what happened is that they discovered a cool new strategy that even the researchers didn't know about, where it kind of like passes the ball through a little tunnel on the left and then can solve the game much more efficiently. So that was really cool because that was the first demonstration of AI discovering something that's that the researchers themselves didn't know. And you can see here, so this is now DQN trained, and you can see that it can play all of these Atari games better than humans. So, and you can see that the games are very different from each other. So they have very different visuals, very different goals, very different controls. And by just observing the pixels and getting the score as a reward, the agent was able to figure out how to play all of them. Right. So after DQN, the next big algorithm that really defined DeepMind, you might argue, is Alphago. So Alphago, as I mentioned, is an algorithm that plays an ancient Chinese game of Go. The rules of the game are very simple. Essentially, there are 2 players. They put white and black stones on the lattices of this of a board. And the aim of the game is to kind of surround as much of your enemy's pieces as possible. The thing is with this game is even though the rules are very simple, it gives rise to huge complexity, and it's very hard to evaluate kind of who is winning. It's very hard to strategize this game, and in China and Korea, like where this game is really popular, it's seen almost as an art form rather than a game necessarily. And a lot of the play is done by intuition. So if you ask a master of Go why they placed the stone in a particular place, often they would not be able to explain why. They will just say that it felt right. And the reason why this game has been kind of this big challenge in AI is because, unlike chess, which you may know got solved in 1997 when Deep Blue from IBM beat Garry Kasparov, the the branching factor, essentially like how many possibilities there are at each to make the next move at each point, is much higher in Go. So essentially, if you evaluate every possible move you can play, there are more possibilities than there are atoms in the universe. So what that means is, if you're an algorithm and you're in a particular state of the board, like at the top of this tree, and you have to figure out what to do next, typically what you would need to do is kind of like play out every possibility to the end of the game, then figure out which of the possible choices gives you more chance of winning, and then play that move, right? But as I said, evaluating exhaustively this whole search tree is basically impossible for Go. When faced with these situations, what is typically done is something called Monte Carlo tree search, where rather than exhaustively evaluating the whole tree, you would essentially evaluate kind of like a few paths through it, and you would pick the moves in each path by kind of like randomly drawing, kind of randomly sampling a move. And then you kind of like do a few of these sample rollouts, and you would average which move is likely to be a good one. But even this strategy doesn't work very well because the tree is so wide and so deep with Go. So it's just computationally intractable. So the way AlphaGo managed to go around this and effectively surprise everyone by beating world champions is by introducing two neural networks. One is called the policy network, and the other one is a value network. So what a policy network does, so it's trained on millions of human professional games, and it takes the board state and it tries to predict a few most likely moves that humans played in similar situations. And what a value network does is it looks at the state of the board, and it tries to evaluate it, kind of tries to predict who is going to win, the whites or the blacks. And again, you can train it by using past games from professionals. And actually, in the original AlphaGo, these networks were first trained using the professional games, but then they would get trained more and more by just evaluating AlphaGo's games against itself. So essentially, it would then kind of train through self-play against itself. And in the next version, in Alpha 0, even the pre-training step was removed. So the game was essentially, the network would start from nothing and it will learn how to play all by itself. So what these networks do is they reduce the width and the depth of evaluation. So when you do this tree search, rather than having to go all the way to the end of the game, you can actually just evaluate a few steps and then use the value network to predict who is going to win, right? You don't need to actually run the game to the end to know who is going to win. And the policy network reduces the breadth by saying that, okay, rather than trying every possible move from one particular position, we take a subset of maybe 10 most promising moves that would have worked well in the past, and let's evaluate only those. And obviously, these two steps reduce the computational complexity a lot, and this is what led essentially to the win by AlphaGo against Lee Sedol, who was the world champion at the time, or one of the best players in Go. And that was a very, very exciting time to be at Deepmind. But the thing is, even though we've had a lot of success with AI, and obviously it's not just Deepmind, you would have heard of all the successes with self-driving cars, with image classification, with kind of machine translation. There are still quite a lot of problems with deep learning. So we haven't solved AI yet. One of the open problems is that these networks are quite brittle. So this was demonstrated by Zagady in 2013. and this problem still hasn't been solved. Let's say we take an image classifier, so you give it an image and it tells you what's in it. And we now have systems like this which work better than humans, so that they can identify and classify different breeds of dogs and cats, and essentially split images in 1,000 different categories much better than humans. So you give this image, this network, an image of a dog, and it correctly obviously identifies that it's a dog. But what you can do is augment it with a tiny bit of noise. And this noise is kind of selected specifically for this purpose. But essentially, to any human, the resulting image is pretty much exactly the same as the original. But such adversarial noise can actually create big problems for neural networks. For example, it might misclassify this image as an ostrich. And obviously, this can create huge problems for using these systems in real life, because if you put an artificial vision system like that in a self-driving car, and it kind of misidentify a stop sign as some other sign, obviously it can lead to catastrophic problems. Another thing is kind of a lack of common sense and real conceptual understanding of what's happening. Again, this is a demonstration from quite an old paper, but it still stands. Here, this model was trained to provide image captions. And you can see that it has a very nice language model. So the captions that it provides, they read well, they're understandable. And also they definitely do relate to the images, but they don't actually capture exactly what's going on. So the image on the left is captions an airplane is parked on the tarmac at an airport, and the one on the right is a group of people standing on top of a beach. So obviously this model doesn't understand kind of causality, consequences, kind of emotional state of people. It doesn't understand physics necessarily. So there's still a lot of work to be done. And when these questions arise, of like, how to address the standing limitations of deep learning algorithms and deep reinforcement learning algorithms, it seems like the consensus is that unsupervised learning might be useful. So yeah, if you listen to Jan LeCun or Yosha Bengio, essentially, or Jeff Hinton, kind of all the essentially godfathers of deep learning and machine learning, that's the story that they're all telling right now. And essentially what we want is an algorithm that can learn about this world the same way as babies do. So you can see here that this baby is not getting any supervision, but it's happy to explore, learn about how the world works, so that when supervision does come, and it actually needs to learn the meaning of words or how to do something useful in the world, it can do so much faster and much more robustly than deep learning systems. So this is where my work lies as well. So I work on unsupervised representation learning. And when it comes to unsupervised learning, one thing is that it's actually a very vague thing to do. So like, if you don't have some sort of ground truth supervision that you're trying to aim at, what do you do? And when it comes to such open-ended questions, one approach at Deepmind is to look for inspiration at other fields. So in my work, I look for inspiration in neuroscience and physics, but also we have to think about linguistics, because, for example, language is a really important part of what makes humans intelligent. So it's helpful to think about its properties and anything we can gain from that to help think about what kind of representations our agents should learn. And of course, the mathematics is kind of like the fundamental thing that underlies kind of understanding in our neural networks. So my work in particular has to do with the idea of disentangled representation learning. So what that means is without any supervision, by just observing the data, we want to figure out what transformations kind of like give rise to that data. So for example, if we observe different geometric shapes, then we can probably figure out that these shapes can be generated by specifying the the shape itself, maybe the color, the position of these objects. So here's an example of a disentangled neural network. So we have a scene of a 3D scene with objects inside, and by just kind of trying to train an autoencoder-like architecture that takes the input and tries to reconstruct it, but with particular regularization inside, we get single units inside this network that control kind of like interpretable aspects of the environment. So for example, if we modify the value of one of these units and then try to reconstruct, we see that it only affects, for example, the color of one of the objects, or its size, or maybe horizontal or vertical position. So this is still ongoing work, but you know, this work it takes a lot of inspiration ideas from physics and neuroscience, and also recently we were able to show that this kind of representation actually matches very well the representations to the same data in monkey brains. So it was very exciting to see that a model that was inspired by neuroscience is now also validated against the real brain. And these kind of models have been shown to be useful in solving some of the problems with deep learning, such as data efficiency, generalization, fairness, the ability to do abstract reasoning and transfer. And the reason for that is because we are learning a representation where, as I said, different transformations are kind of pulled out to be very explicitly represented inside the network. So then it makes it very easy to kind of ignore things that are irrelevant for the task and then easily generalize over it. And also pull out, like normally tasks would be very they would relate to some of these properties that are extracted in the representation. So we can then learn the mapping between the representation and the task much easier. So for example, we show that an agent that learns a disentangled representation that kind of factorizes some latents that correspond to the environment or the objects is able to generalize to new tasks much better. So if it's trained to pick up cans and ignore hats, and also pick up cakes but ignore balloons in the environment with a green wall, and then it's tested in the environment with a red wall, it can immediately solve that task, whereas the baselines without disentangled representations can't do that. So that's kind of the end of the science part of the talk, and I just want to finish with a quick story of my journey to Deepmind, and I'm going to start very far back in Russia, where I grew up. So this is me and my brother, and my brother was always very much interested in programming, and I kind of tagged along and started programming early on as well. But when it came to deciding on career options, my brother was very resolute on studying computer science, but for some reason, for me, it felt very dry and kind of not particularly appealing. So I thought maybe I should be a doctor instead, because I was quite good at biology. But this is where the angry mob of kind of the friends and family started to say, well, you know, being a doctor is not a career for a woman. you have to study for a long time, you have no life, so maybe you should consider doing psychology instead, because it's kind of like being a doctor, but you can still have a life. I was quite easily persuaded at the time, so I did move to London and started studying psychology, whereas my brother moved to Oxford and started doing computer science as planned. And he was very happy there, but I realized that actually psychology wasn't really for me, and I wanted to do what my brother did. And this is kind of, I think, one of those moments where it was quite hard to know how to switch from psychology back to something more computational and mathematical, given that essentially my degree had no maths in it at all. But I managed to find a lab at Oxford, which was called the Oxford Foundation of Theoretical Neuroscience and Artificial Intelligence. I didn't know what they did, but the name sounded cool, and I managed to persuade them to take me on for kind of like a year out to do research. So I managed to join my brother, and I started working with biologically plausible neural networks. So they used Hebb rules and they used spikes. So they were very different from the neural networks we use in machine learnings. And I tried to figure out how vision and hearing perception develops in the real brains. And at the same time, I also did spend way too much time on hobbies like playing poker or rifle shooting or ballroom dancing. I also did quite a lot of internships because I still didn't really know what I wanted to do with my life. So I tried becoming a quant, and I interned at Deutsche Bank, Goldman Sachs, and Orbis. And then a friend said, well, you're doing a lot of programming in your PhD. Why don't you try Google? And I was very lucky to get into Google research for a summer. And that was the year when Google acquired Deepmind. So they introduced me essentially to Deepmind. And once I interviewed and realized what Deepmind was about, there was no question anymore. That was exactly where I wanted to be. So finally, my story had a happy ending. So on this, at this point, I think I should stop, and I think we still have a few questions, some time for questions.
Okay, thank you so much for this fascinating talk, and thank you so much for sharing your experience. I'm learning because I did not know the details about your career, and thank you for sharing this. Actually, there are like 30 questions, but
Wow.
we will not have time to go through all that. I will share quickly the screen, and maybe we go just through a few of them, and then we will continue answering them offline.
Sounds good.
I will just pull out now the questions. Okay, can you see my?
Yes. So shall I start from the top then?
Yes. So yeah, the first question, most popular one: what are the differences between Google Brain, Google Research, and Deepmind?
Right. So I've been at Google Research and I've been at Deepmind. I have quite a lot of friends at Google Brain, so I guess I can tell the differences. So Google Research is very much embedded within Google, and essentially it's all about making Google's core products work well and work at scale. If those products require some sort of machine learning, I guess when I was interning, actually, it wasn't even necessarily about machine learning, but now a lot of it is about machine learning. Google Brain is very similar to Deepmind in terms of its more research oriented, it's more open-ended, but it's still, like, compared to Deepmind, it's not so much focused on AGI, right? So at Deepmind, we really want artificial general intelligence. We use reinforcement learning a lot, and we use games a lot, whereas at Google Brain, the research is maybe more diverse and there is less focus necessarily on deep RL.
Okay, thank you. Is PhD title essential for a career in research in Deepmind? How many PhDs versus non-PhD are in your team?
So PhD is essentially if you want to be a scientist, but it's not essentially if you want to do research. So we have research engineers, and for that you don't have to have a PhD. And depending on the team, a lot of the time, the work that's actually done in practice is the same between research engineers and research scientists.
What red flags and green flags do you consider in hiring the person?
That's a good question. So I think it's very personal. For me, green flags is kind of like this ability to take a lot of ideas from different fields and kind of play with them and brainstorm. So in my interviews, I try to ask a question that the person probably wouldn't have thought about and see how they deal with that. And the red flag is essentially lack of collaboration. I've interviewed some people who essentially said, I'm amazing, I don't need to work with anyone, and this is not what Deepmind is about, where our work is very collaborative, so you need that.
Is it possible to do internship or fellowship research during PhD? And if yes, in which countries and what is the procedure? Maybe this is a bit longer, but yeah, please try.
So it's definitely important, possible to do internships. As I said, I've done 5 or 6 myself during my PhD, and I think actually I would strongly encourage you to do that, because for me it was the most invaluable experience I think in my life, to be able to be there and see what the different companies are like. And even in finance, I did 3 internships, and you would think that the job is the same, but it wasn't. And the feeling in different companies and the way they operate is very, very different. And I think you wouldn't be able to know if it's a good fit for you until you go and try.
Okay. Maybe we end with this one. I want to do fundamental research in AI. What should I prefer, academic institutions or Deepmind, and why?
So I think there are pros and cons in both. I can say that Deepmind is great because it's very fast-paced. It's very kind of exciting to be there, and you have basically amazing people who all speak the same language, who are all interested in the same things, and you will get so much support that I think it's very hard to get in academia, which often is a little bit more fractured, and it's like the pace is a little bit slow. So for me personally, I didn't necessarily want to stay in academia because I found it too slow. But when I joined Deepmind, I felt so energized and excited to work that it completely changed my perspective on academic research.
Okay, and this one is really the last one about internship opportunities.
Oh, so we definitely have internship opportunities. You should apply on our website, and you can also probably contact me or Viorica or anyone else at Deepmind who can help you with your application, maybe refer you directly.
Yeah. Maybe we should just mention that the internships are on hold just for this month of pandemic, because we Deepmind does not want internships remotely, because as Irina said, it's important for you to come into Deepmind and see the environment and collaborate with the people, which you would not get in a remote work mode. So the internships are now put on hold, but they will resume as soon as this situation gets solved. Okay, so I think we will stop here, but there are still quite a few questions, but we will